Hello, everyone. My name is Jiarui Liu from Carnegie Mellon University. Today, I will be presenting our paper, Automatic Generation of Model and Data Cards, a step towards responsible AI. This work is a collaboration between me and Wenkai, under the guidance of Zhijing and Professor Mana Diab. First of all, what are model cards and data cards? Model cards and data cards have been widely used as documentation tools to provide crucial information about models and datasets. They are essential for discoverability, reproducibility, and sharing. For instance, on Hugging Face, you can find a collection of models and datasets along with their cards. A model card typically includes a brief description about model, its intended uses, potential limitations, training parameters, procedures, and evaluation results. A data card includes a description of the dataset, the source data being used, dataset creation procedures, intended uses, limitations, and potential biases. Currently, model cards are written by humans. Even though Hugging Face provides detailed specifications and guides, it still leaves the decision of what to report up to developers who created their models and datasets. This reliance on developers' subjective choices often reduces the quality of these cards. As shown in this figure, many model cards miss important information and can be hard to understand without consulting the original paper or code. Moreover, developers tend to use existing cards as templates, which can perpetuate inconsistencies. This has led us to design an automatic generation pipeline to provide standardized, consistent documentation for models and datasets. So in summary, our work offers several key contributions. First, we introduced a novel initiative to systematically use large language models for automatic generating model and data cards. Second, we released the Card Bench, a curated dataset of papers and GitHub READMEs referenced in model and data cards from Hugging Face. Third, we proposed Card Gen, an approach that breaks down the card generation task into multiple subtasks using a two-step retrieval process. Fourth, we developed a new set of quantitative and qualitative evaluation metrics, performing both automatic and human evaluations to show the effectiveness of our approach. Our code and data are available at this URL. To create our card bench dataset, we identified the model and dataset pages on Hugging Face as our data sources. We crawled the model and data cards for the 10,000 most downloaded models and datasets, respectively. This resulted in 4,800 non-empty model cards and 1,400 non-empty data cards. For future evaluation, we constructed a high-quality subset, including 294 model cards and 300 data cards. Additionally, we collected the corresponding papers and GitHub repository README files for each card. The statistics are shown in these two tables. Here is an overview of our card gen pipeline, which includes a two-step retrieval process followed by generation. To create a full model card, we start by listing comprehensive questions about the model, such as its evaluation metrics and potential limitations. Then, we use large language models to infer relevant sections or paragraphs, which we call as our first retrieval step. Inspired by previous work, we also generate pseudo answers for each sub-question, using the large language model's own knowledge at the same time. These pseudo answers act as a query to retrieve relevant document chunks, which we refer to as our second retrieval step. Finally, we use a large language model to generate answers for each question based on the highest ranked document chunks, and then concatenate these responses to form a complete model card. So how do we build our question list to fully complete a model card? Following Hugging Face guidelines, we define 7 sections with 31 questions for a model card and 21 for a data card. The key questions highlighted in the table below cover model summary, description, direct use, biases, risks, limitations, and evaluation results. We assign specific roles to answer each question, ensuring the model's strongest instruction following capabilities. We incorporate both human and automatic evaluations in our setup. So the human evaluation is crucial here for 3 reasons. First, no ground truth labels. Card generated model cards lacked ground truth labels, necessitating manual evaluation. Second, incomplete human-generated cards. Current model cards by human developers are often incomplete and deviate from the recommended template by Hugging Face. Third, length and complexity challenge. Large language model generated model cards are typically over 4,000 words, pose challenges for open source standard evaluations with limited context size and costly GPT-based metrics. So we randomly sampled 50 model cards from the test set and evaluated the following 7 models: Cloud 3 Opus, GPT-4, GPT 3.5, Llama 2 70 billion, Vicuna 13 billion, Llama 2 7 billion, and Mistral 7 billion. Our evaluation uses 5 metrics: completeness, accuracy, objectivity, understandability, and reference quality to thoroughly compare generation quality. The results show that Cloud 3 Opus, GPT-4, and GPT 3.5 outperform human-generated content and other open source models in completeness, objectivity, and understandability. However, human-generated model cards generally excel in accuracy and reference quality. For automatic metrics, we classify them into categories based on the relationships among the tuple of question, retrieval text, and generated text. First, we evaluate the factual consistency between the retrieved text and generated text using 4 standard metrics: Roach-L, BERT score, and scores outputted by an NLI fine-tuned model. Additionally, we use GPT-4 to assess 4 other metrics: faithfulness, answer relevance, context precision, and context relevance. So in this table, we present the factual consistency evaluation results per section using 4 standard metrics. There's no uniform trend for factual consistency across all subtasks. GPT 3.5 outperforms open source models on the uses and biases question sets in nearly all standard metrics. However, Llama 270 billion generates more factually consistent answers on other subtasks according to Roach-L and BERT score. In contrast, in this table, using GPT-4 as a scorer, we see that Cloud 3, GPT-4, and GPT 3.5 outperform other open source models across nearly all subtasks and evaluation metrics. This suggests that GPT metrics provide more consistent evaluation results than the previously mentioned standard metrics. To better assess the effectiveness of our retriever and generator components, we compared our card gen pipeline to 2 baselines. First, we have the one-step retrieval baseline. In this setup, we keep all other pipeline components unchanged, but simplify the retrieval process. Instead of our 2-step method, we directly retrieve the top K chunks without first inferring relevant paragraphs. We measure context precision and context relevance to evaluate retrieval quality for a given question. As shown in the table on the right, the two-step retrieval process consistently achieves higher scores than the one-step retrieval across nearly all models. This results further supports using a paragraph level retriever. The second baseline is retrieval only. After completing the two-step retrieval and obtaining relevant chunks, this baseline directly uses the retrieved chunk as a final output without any generation steps. We use metrics like answer relevance, understandability, and brevity to evaluate the generation quality for a given question. As shown in the table on the right, card gen significantly outperforms the retrieval-only baseline across all metrics. And this highlights the importance of the generation step in summarizing and restating sentences from source documents to enhance their understandability and conciseness. In conclusion, we proposed an effective card generation pipeline leveraging state-of-the-art large language models. We validated our two-step retrieval and generation design by comparing its performance against two baseline methods. Additionally, we found that Class 3 Opus and GPT-4 consistently outperforms the tested open source models. And large language model generated cards excel in completeness, objectivity, and understandability compared to human-generated cards. For future work, we will incorporate more advanced prompting techniques in our generation pipeline and compare them with our current method. We will also explore an iterative retrieval generation framework to refine responses based on newly retrieved text for a more detailed context. Additionally, we will integrate strategies to reduce context conflicting hallucinations. We welcome everyone to check out our paper built upon this work. Thank you for listening.